The heavy water inside of a single glass contains the energy equivalent of a full tank of gasoline. Extracting that energy produces zero greenhouse gases and carries zero risk of a meltdown. Most nuclear power today relies on fission, the process of splitting heavy atoms like uranium. While effective, it leaves behind radioactive waste and carries inherent safety risks. Fusion does the opposite. It forces light atoms to combine. Recreating the core of the Sun on Earth requires building a physical bottle capable of trapping 100 million degree plasma. Without the Sun's massive gravity to hold the reaction together, the heat is difficult to contain. After 70 years of melted reactor walls and fizzled reactions, the field is reaching a turning point. A sudden convergence of artificial intelligence, advanced material science, and private capital is cracking the foundational physics of the fusion equation. This is the Lawson Criterion, the mathematical threshold for net fusion energy. It multiplies plasma density, tightly packed fuel, and ion temperature, the heat forcing nuclei to collide. The third variable, energy confinement time, measures how long plasma is held stable before losing heat. Achieving all three parameters simultaneously is the only way to ignite a self-sustaining miniature star. Modern technology is now being deployed to target each variable individually. The most efficient fuel for this reaction is a mixture of deuterium and tritium, isotopes of hydrogen that contain extra neutrons. Because these nuclei carry the same positive charge, they naturally repel each other until extreme pressure forces them to lock together. To reach the densities and temperatures required for fusion, researchers use two primary types of macro machines. One method is inertial confinement. This involves using arrays of the world's most powerful lasers to compress a tiny fuel pellet to stellar densities in a fraction of a second. The other method is magnetic confinement, which uses massive, donut-shaped magnetic cages, known as Tokamaks, to trap and squeeze the fuel. While humanity can now routinely reach 100 million degrees, sustaining the reaction depends entirely on keeping that chaotic plasma trapped. Superheated plasma is highly volatile. If it deviates even slightly and touches the tokamak walls, the reaction instantly cools and dies. To manage this volatility, Google DeepMind and Commonwealth Fusion Systems created the Tokamak Plasma Simulator. Tokamak is a fast, differentiable program designed to model how heat and matter flow through the plasma core. Deep reinforcement learning allows AI agents to run millions of virtual experiments, learning how to perfectly tune the reactor's magnetic coils in response to different conditions. These AI pilots can react to the plasma's movements in milliseconds, constantly adjusting the magnetic cage to keep the fuel suspended. Shifting plasma stabilization into a software optimization problem allows reactors to maintain confinement with a precision that was previously impossible. Fusion neutrons bombard reactor walls, knocking atoms out of their lattice and leaving microscopic voids. To fix this, scientists use high-entropy alloys, adding smaller vanadium atoms to a tungsten base. This creates space, allowing displaced tungsten to slide back, effectively healing the structural damage. Alongside these alloys, a lithium blanket lines the reactor. This layer absorbs the neutrons to breed more tritium, allowing the system to fuel itself. This atomic-level engineering ensures the reactor structure can survive long-term operation, addressing the final physical barrier to a commercial power plant. For decades, fusion research was characterized by sprawling, government-led experimental projects like ITER. Today's landscape is moving much faster. Private enterprise has taken over the race. Over 50 startups have secured upwards of $7 billion in capital to build commercial-scale machines. Major corporations are already signing power purchase agreements, committing to buy fusion energy to power their massive infrastructure. Fusion has transitioned from a purely scientific pursuit into an industrial engineering challenge. The era of fusion being perpetually 30 years away is ending. We now have the tools to plug the power of the stars directly into the electrical grid within the next decade.